I'd like to introduce our next speaker, Katherine Kuchenbecker from the university. I'm going to talk about haptic intelligence in robotics. Katherine's associate professor actually of mechanical engineering and applied mechanics at the University of Pennsylvania. Katherine.
Thank you so much, and thank you everyone for inviting me and giving us a chance to talk about some of the work we're doing. I hope you start to see some consistent themes through the many talks, and so I'll try to build on what the other speakers told you. I want you to, all of us agree here, we think robots play a big role in the future, and in order to help people, they're going to need to do stuff in the real world. Like, we want robotic helpers that can reach out and pick up objects, that can clean up our kitchen, that could take care of elders. So I want you to imagine for a moment we have a robot, and we want it to do something like pick up a match and light it. All of you could do this task very easily, and you've done it, or pick up a candy from the bowl and unwrap it. I want you to think for a moment, do you think you could light a match if your hands were numb, if I took away your sense of touch? So what do you think? I have a video to show you. This is done by Professor Roland Johansson, who's a very famous professor of physiology, neuroscience of touch in Umeå in Sweden. And he's anesthetized, for research purposes, the thumb and index finger and middle finger of this woman. Now, she has full vision. She can see exactly what's happened. She's lit matches many times before, but now she has no sense of touch. And I want you to notice how clumsy, how repetitive and awkward, and I'm sure frustrating this probably was, but she's doing it. She's able to do it. She's using vision. She's watching the context very carefully, but it took her like 6-7 times as long as if she had been able to feel what was happening. And that's because the physics, the interaction between our bodies and the objects we hold and the things in the world, they can change, the forces can change very quickly, and there's a lot of intelligence and reaction that goes into accomplishing physical tasks every day. So these kinds of problems really fascinate me, and so I think we need to go beyond vision and beyond hearing, audio, and really think carefully about your hands and your sense of touch. And so we take a lot of inspiration in my group from what is known in science, from neuroscience, to try to endow robots with a better sense of touch. You might not know much about your sense of touch. It's less understood than vision and audio. There are 4 different kinds of cells, mechanoreceptors, in your fingertips, and they have different spatial sensitivity and different temporal sensitivity. So there's some fast adapting ones, some slow adapting ones with broad receptive fields and ones with narrow receptive fields, as well as temperature sensitivity and pain. And all of those signals come together and also are fused with your knowledge of the pose of your body and the efforts, how hard your muscles are working. And it's a very tight feedback loop. There's a lot of interaction between what you do and what you feel to let you understand what it is you're touching and whether you're having the effect on the world that you want. And so this area in which I work is called haptics. It's a sort of a burgeoning field within the overall robotics, and it has a lot of connections with neuroscience and psychology. And so we study how humans and robots interact with physical objects through contact. My training is mechanical engineering, and so physics matters, and now we want to endow robots with a sense of touch. I think robots right now, it's very difficult to do that task I showed, pick up a match and light it. I work in the University of Pennsylvania, which is in Philadelphia. We're a very old university for American standards. We were founded by Benjamin Franklin, and I'm part of what's called the GRASP Lab. It's one of the leading robotics universities in the world, and actually we're hiring this year, so if anyone knows any talented postdocs or PhD students, we are hiring. We'd love some faculty, new blood, new professors. Here's a bunch of projects that I've done in my lab. I've been a professor at Penn. This is my 9th year. So here are a whole lot of different things. We design and build new interfaces for people to use. We do a lot of haptic rendering for people to feel sensations. Today I'm going to talk more about our robotics work with teleoperating, controlling robots from a distance, and autonomous robots. We do also some assistive technology. But the point I really want to make today is that autonomous robots could truly benefit from having some haptic intelligence. There's a long history in robotics of vision and reasoning, and we need that. But to do useful work in the world, robots are going to need a sense of touch and some intelligence around that capability. And so you might wonder, well, hey, why don't modern robots have a good sense of touch? Why don't they have haptic sensing? And I came up with 3 explanations, and I'm going to give you some examples. We're just going to go through them in order. The first one is that if you ask the average roboticist, like, what is haptics? Like, what would it mean to have haptics or touch feedback in your robot? Most people would equate sort of touch, being able to feel with the world, with a force sensor. This is an ATI force sensor that can measure 6-axis forces and torques, and they're lovely. And often they'll be mounted. This is a PR2 hand that has been transected and placed one of these sensors right in between the forearm and the hand. But these sensors are expensive. They're $6,000, maybe more than that. And they're delicate. You crash one time into the table and it's broken. You need to get a new one or get it replaced. That makes people very nervous about using these sensors. And they tend to drift. Physical sensors, everything responds to temperature. So the kinds of signals you get can be a little annoying. And then lastly, you have to mount them in series. You have to basically break your robot and put this in there. And then if you have anything going on beyond there, there have to be cables going through it. And I think this has been a big deterrent, that people haven't wanted to make the investment and have the chance that it will break. And so we'll just go without. We'll just have robots that have numb hands, and we'll just see how well we can do. Maybe we'll crush some stuff. It's okay. But I think that haptics and the sense of touch is actually a lot more than just a force vector and a torque. And I think we need to start acknowledging that and looking into lots of other clever sensors that might be emerging in many other areas and bring them into robotics. So I think we need to think beyond these force sensors, and in particularly to looking at tactile cues, those cells that are in human skin. I didn't say we have a 6-axis force torque sensor at our wrist, right? We have skin and muscles. And so we should probably emulate that. And to motivate that, I'm going to give one example of work that I did over many years in the area of robotic surgery. So this is a teleoperated intuitive Da Vinci robot. We have one in my lab. The surgeon sits over here and remotely controls long, thin tools that are inside the patient through tiny incisions. And the surgeons, if you go talk to them, Penn has a big health system. I work with many of the surgeons there. They love the visualization. It's 3D, so they can tell depth better than laparoscopic surgery, where they're just looking at a 2D image. And the instruments have these little wrists that are driven by cables, and they can learn to do surgery very well in a minimally invasive way. What you don't have, what you give up if you use the robot, is you have no sense of touch. The position commands from the user are sent to the robot, but no information flows back to the user aside from vision, what they're seeing. And so they have to learn to feel with their eyes. They have to learn to see contact and forces. And the camera has a very narrow field of view, and so it's actually quite dangerous when new doctors start learning to operate with the robot. They can inadvertently get tangled up in tissue and smash into it or crush it much too hard and not have the faintest idea they're wielding this very large robot. And so they have to practice, but I think that we could do better than that. And so many people had worked on trying to endow robotic surgery systems with a sense of touch. I came about it from a much broader standpoint. Almost everyone else had been trying to think force. Let's try to, how can we engineer a force torque sensor, put it in the robotic instrument? It has to be sterilizable, it can't cost too much, and it has to be robust, it has to be redundancy. How can we let the person feel it? There's all these closed loop control issues. It's a very technically challenging problem. And I said, hey, let's just think a little more broadly. The sense of touch has many aspects to it. It's not just force sensing. What could we do that's technically feasible and clinically viable, something in the near term that we could actually put in an operating room and have a surgeon, maybe a new surgeon, have some extra sensory feedback to improve. And so again, we go read papers about how the sense of touch works. We look at those 4 different kinds of mechanoreceptors. Which of these should we be paying attention to? Most of the work in surgery is done holding instruments, cutting tissue, dissecting, suturing, and so you're not actually touching the tissue. I'll talk in a minute about bare finger touching tissue, but you're often holding an instrument, and it is well known in the neuroscience literature that the mechanoreceptor that you need to do this kind of interaction is actually one that hadn't been used much or thought about much in robotics. It's FA2 Pacinian corpuscles. They are like little biomechanical accelerometers that detect vibration over a really large field. I don't need to know the details of how the tool is touching my fingers. I'm just dragging or cutting or probing in the world. And the contact forces and vibrations travel through this rigid object into my fingers, and I know, and then I can tell what's happening. And so we have focused on vibration starting several years ago. Instead of going after forces, we said, let's see, I think there's some useful information about transients, making and breaking contact between the instruments and the surgical environment. So let's look at vibrations. And so over several iterations, we created a system that we call VeroTouch. This is just a research project. There's no company or anything, but we have this set of components that we fabricated that we can take into an operating room or onto our robot and attach it and add sort of an extra feedback channel. So everything, the motion control, all happens the normal way. We just add an extra set of measurements over here and an extra set of cues for the surgeon to feel. And we designed it to be very, very natural and very simple and inexpensive. And so the sensing side, we use a high bandwidth accelerometer. It's a MEMS-based technology, 3-axis high bandwidth. These cost about $10. Robotics stands to benefit hugely from advances in sensing from mobile devices and embedded systems. And so there's been a lot of crossover from cool new sensors developed for mobile devices and bringing them into robotics and saying, what could we do with them? So this is one example. We started using these several years ago, and we attach them up on the robot outside of the sterile field, so they get bagged. They can stay on the robot all the time. And they enable us to measure what's happening as the surgeon is operating down here. Contacts travel up, and we can measure them, almost like a microphone, but lower frequencies that you can feel. It works for any instrument. The surgeons are always changing out scissors or a scalpel, and we don't need to sterilize the sensing. It just stays on the robot all the time. And once we have these right and left instrument vibration signals, we can allow the surgeon to feel them, and we developed an actuation system for that. It's like a speaker. It's just an electromagnetic coil, and then inside it is a permanent magnet. And I'll show you a picture. These cost a few $100s, but they're seriously very, very inexpensive also. And so this is my main surgical collaborator, David Lee, who's done thousands of robotic prostatectomies. In one of the experiments that we ran, we attach these motors, its actuators, onto the handles that he's using to control the robot. And you can see when something happens, when there's an impact on the instrument, this little silver piece vibrates back and forth, tracking the signal. And he can then feel it with his fingertips, which are very sensitive. And then he can tell what's happening. And it feels very realistic. It almost feels like you are holding the tools themselves. And it doesn't get in the way. It doesn't destabilize the whole robotic system. And so when you put it all together, the surgeon is sitting at the console and moving the instruments, and across the room, they're doing this procedure. And we're able to measure signals and let the surgeon feel them. Now, I'm bringing this all back to autonomous robots. I think teleoperation is an intermediate waypoint towards getting to see how could we make an autonomous surgical robot? What kinds of things would it need to be able to do? I think we would also want to pay attention to this kind of signal. Oh, and here's a video of what the surgeon was doing. And let's see, can you hear? There's some audio that we'd like to be able to hear. Yeah, there we go. So now I'm playing as sounds the vibrations that we're measuring on the left and right instrument. And you can see every time there's a transient in contact between the right tool or the left tool, or this is a little practice board. And this is actually not a very good surgeon. This is someone in training. They're kind of crashing around. You might not want to let them take your prostate out. So they're a little tipsy perhaps, but it's a good example video because it shows what happens that when you hit things, we can measure that, we can let the surgeon know, and then they can adjust how they're operating. And these are, I think, the kinds of signals that you would want to measure and react to if you were an autonomous robot, or some of these kinds of signals in order to do this task on its own. We've done a lot of study on this just to show you a few more things to validate that this idea worked. We looked in real surgery, not just plastic toys. I'm going to show a real surgery video, so I warn you, there will be blood. You may want to look down and avert your eyes for a moment. This is an experiment on a pig, a porcine model, and this was our first in vivo test of this system with haptic feedback on a Da Vinci. And we're able to see, actually there's sound on this also, I'm not sure if it's playing, but you can see the signal strolling across. That as the surgeon is operating, we're able to pick up these cues, these transients, and play them for them. So this was like the first surgery ever done with haptic feedback. Here they are now tying a knot, and there was a little collision between the instruments, and we can measure that, and so they know a little bit more what's happening. Now they're trying to pull the knot through, pull the string through. These are little detailed interactions that are difficult to do without a sense of touch, and it improves it if you can feel what's happening. Okay, so that's enough surgery video for you now, I bet. Right before lunch. I apologize for that. All right, surgeons are also quite opinionated. My father's a surgeon, and so anytime you're developing new technology for health, you need to get buy-in from the people who are actually going to use your system. As an engineer, you can say, oh, it's wonderful, but it really needs to better their clinical capabilities. So we've also done a lot of testing of surgeons coming in to try it, not just our collaborators. So we took our robot a couple years ago to a big conference in Baltimore, and then for days, my students just ran demos and had people come in and try it, and they got to fill out a little survey when they walked away. And they tried either this pig transfer, they tried pig transfer, this little practice skill, and sewing, suturing on a fake tissue. And then we had 94 people who agreed to do the survey, mostly surgeons and residents, people in training. And we asked them, do you think this kind of haptic feedback would be useful? And all of them said yes. It's the best pie chart I've ever had the honor of making in my scientific career. I think the reviewers might say, you don't need that pie chart. It's obvious, but I can put it in my chalk. Look at that. Everyone said, yeah, haptic feedback is nice. I like it. We also were playing the sounds like you heard, and they could feel it in their fingers. And we say, which one do you like better, the sounds or the feeling, or what would you use? And most people wanted both the sounds and the feeling. Some people only wanted the feeling. Basically, like 2 people said they wouldn't turn it on for themselves. These were very experienced surgeons that they said they wanted it for their new trainees, their residents, to learn how to operate. So those are some points. Last thing, this actually is a last little point on this project. This is a quiz. I want you to watch this video and tell me, do you think this is an experienced robotic surgeon or someone who's more of a novice, a newbie? What do you think? Would you let this person operate on you? No, right? No, but how can you tell? You're picking up on a lot of different hints of how they're moving. They're a little clumsy. And so no, it's definitely a novice. And now I want to show you the same video. There's no sound, but you can see the plots on the right and left side. And you see when they're clumsy with the physical interactions with the world, they're causing giant vibrations on the instruments that we can now measure. These had never been measured before. And it turns out they have a lot of information in them about skill, about the operator. And so inherently, if we were doing this for a robot, about how well the interactions with the world are progressing. And this has led to a whole other interesting avenue of research in my lab, where we're now trying to estimate. So now we do practice tasks like this, and we measure the forces and the vibrations that the surgeons cause. And we can rate their skill on their learning curve in different domains. And we can do just as well, if not better, than like a human who has to sit and watch the video and tediously rate it. We can do it just automatically, which is getting really exciting. And so this is my one example to say, sometimes an unconventional idea, different kinds of sensors, other kinds of signals, particularly tactile signals, things you can feel in your skin, can offer huge benefits and be much more practical for the short term for actually implementing on a real robotic system. We need force sensing and force feedback, and robots should probably have force sensors too, but they need skin. And many of our robots don't have skin and can't feel what they're doing when they're touching the world. And so, we need to think beyond force sensors, start thinking about tactile cues. This could mean new sensor development, new integration techniques, and in the end, I think could deliver a lot better capabilities. Now, once we have sensors that can measure physical stuff on robots, not just cameras, and what are we going to do with those signals? Because these kinds of sensors are unusual and not included on robots, we don't yet have nearly as sophisticated of techniques for dealing with that data as we do, say, imaging data or depth data. And so if you gave a plot or had a force sensor on your robot, the most common thing someone would do is just threshold it. Just say, oh, is it greater than a Newton or less than a Newton? Then I guess it's touching something, or that robot's probably not touching something. And this, I think, is very wasteful. This is simple, it's easy to program, fine, you can test it out, but you're throwing out so much information. There's so much subtlety and so much useful cues in the data that you're able to gather. And I think we need to get more sophisticated in how we're handling haptic data. We need to dig deeper into these signals. And so I do a lot of work with the PR2. This is a research robot. It has 2 arms and hands, and it can drive around, but we mainly use it for manipulation research. When we first started using the robot, we found it would, the default controller was just 100% motor effort, close the gripper as hard as possible to grab something, try not to drop it. It was a menace. It would just destroy objects all over the place. It would shatter, it would just crush everything. It would shatter glasses and cut itself, and didn't have the faintest idea that it was doing this. But it does have some tactile sensors, which we figured out how to make use of. It also tended to be pretty clumsy in its interactions with the world. So you make a model of the world, but there's going to be some miscalibrations. And here the robot's trying to set this can down on the table, and it's misjudged just by a couple centimeters in either direction, it ends up looking very clumsy. And because it's not paying attention to any of the physical contact cues, it's just putting its arm out there and letting go and say, I hope that bottle is, or that can is right on the table. And it's usually not going to be. We want robots that are better than this. So how do you accomplish that? Again, we take inspiration from the human sense of touch. We read lots of neuroscience papers. Again, Roland Johansson, this is a Johansson and Flanagan article that I love, on how humans coordinate the use of tactile cues over a very simple picking up and setting down task. And you can see certain mechanoreceptors fire at different key times where you need to change the type of controller. When you're moving through free space versus you're contacting and you need to react. Or you're trying to hold something and not drop it, and detect if it's slipping through your fingers. And so you need to have that intelligence to react to certain kinds of events and in a smart way. And so we did that just with pretty basic, again, simple sensors, not thousands of dollars, just what's inbuilt. You can measure the gripper position, basically how open or closed the hand is. There's one accelerometer. Luckily, the people who made this robot heard me give a talk at a conference many years ago where I was extolling the virtues. I was showing like the very preliminary data of that robotic surgery project, saying how wonderful accelerometers and transients were. And so they put a $10 accelerometer in the robot hand, and we were really delighted that it was there so we could start taking advantage of it. And then there are also some pressure sensing cells on the fingertips. They're pretty simple. You can pull them only 24 times a second. And then we wrote a controller. You don't need to know the details except that instead of just thresholding the signals, we do other things. We filter them to just look at the quick changes or to only look at the slower values. And then also doing closed-loop force control and position control based on these tactile pressures, or changing the gains on the robot based on whether it's holding something or not, adjusting the physical interaction, and having these state transitions. And you can get much better behavior and get really nice output. So here's a robot trying to pick up an egg. Now, if you just program this 100% motor control close, you would crush the egg, no problem. But no eggs were harmed in the making of this video. The robot reaches out, and again, this is actually kind of on the smaller end of objects that the robot can see and find, so it had to readjust based on where it felt the contact happen first, and now it's going to reach in there and close and detect contact and very quickly stop squeezing, but try to just maintain the right amount of pressure on the object so that it can pick it up and hand it over or do something else. Here's actually the same algorithm, but the second half of it. Let's now try to set this object down. Instead of just blindly smashing, we move down until we feel the object slip just the tiniest bit in the fingertips or just the tiniest jostle in the wrist. So when you're paying attention, I know I'm going to touch, but I don't know when it's going to happen. And when it does, I know what to do. I need to open my hand. And you can get much more intelligent looking robot movement control than if you do it without a sense of touch. And we've done testing with lots of different objects and showing that we can hold them well and not drop them and not crush them because robots are going to need to deal with objects that they haven't encountered before. There's a huge variety of things in the world. This is the other little piece I wanted to show you about palpation. So going back to medical applications, we aren't always using tools. We also probe the world with our fingers. This is very new work that we just submitted a paper on earlier this week, so I thought I'd show you some really new stuff. As a experiment, we put a little biotech, this is a robot fingertip sensor, on a milling machine with a big sample. This is a fake tissue sample that we fabricated with rigid embedded spheres. This is a model for prostate cancer or breast cancer in soft silicone rubber. In their space, you see 5 lumps here. And this is a commercial product that actually spun out of Jerry Loeb's lab at USC. That can measure fingertip shape and pressure and vibrations and temperature all in a tiny package that's the same size as a human finger. It was actually developed originally for prosthetic hands, but we've been using it more for autonomous robots. So we gathered a huge data set where the robot palpated all the way across this sample, and now we're trying to write algorithms that can tell, are you touching healthy tissue just away from the lumps, or is there some tumor? Is this suspicious feeling? And this is what a single probing, palpating feeling looks like. We basically get 20 numbers, and from those 20 numbers we need to decide, is there cancer there or not, just based on a single probe. This is the data spread over the whole data set, that entire sample. It's like 10,260 pokes, and we're looking at, this is the DC pressure. You see the pressure increases right over the lumps. This is 2 different electrodes on 2 different sides of the finger where you see it bulging or impinging. And you clearly see at least the bigger lumps, the first 3 or maybe 4 rows. But the robot doesn't have access to all that data. That takes a long time. We don't want a painful painfully sit there while the robot for 24 hours palpates your body, and then it says, ah, I found a lump. No. We want to do it more like people do. Just press once and maybe twice or 3 times and feel some discontinuities or weird things. So you would really just have a single number from each of these, say the top row of plots. The bottom row is a totally different day. You see a lot of the same patterns, but the values have shifted. It's actually a little bit darker on the bottom and some other variations. And this is, again, coming back to the tactile data. We're not yet to the point, cameras, I think, we're somewhat invariant. Someone makes this camera or this camera, the images look very similar. But tactile data, it can depend a lot more on the conditions that day or on variations that are beyond your control. And so we've been working on algorithms to detect the cancer without needing so much training data. And so this is a very kind of simplistic training, just looking at the values of the sensors, trying to figure out where there are lumps, and we can do a good job. But then when you try to take a model that was built on other data and apply it to this data set, it thinks everything is a lump. It can't tell the difference because it's so tightly controlled. It's learned this very, very specific version of what healthy tissue feels like. And so this is sort of a naive, silly approach, but haptic people haven't really been thinking about perceptual invariance yet. And so we're just starting to do that, and we're borrowing from vision, actually. And so we've been able to get a lot better results. These are still preliminary. But instead of looking at just the value, like, oh, sensor 1 was a value of 107, and sensor 2 is this, we look at the differences, the pairwise differences between what is felt in a little region across the finger, and we're able to get much better transfer to another data set. So models that could be built from one day and then maybe used better in the field. There's still a lot of improvements to get. We finalized the results on Sunday, submitted the paper on Monday night, but I think there's a lot of promise and interest here in trying to do perception from touch for robots to be able to make confident and correct decisions about what they're feeling. Last little thing, I'll go through this quickly. When you start working with touch, you don't realize it, but the robot's own motion causes sensations that the robot will feel. And so we did a lot of work on trying to understand the connection between the movement and the touch, what you will feel. And particularly, I think robots need to do a better job at anticipating what they will feel as they move so that they can distinguish things that come from the world versus from their own motion. And this was a project with one of my PhD students where we're using the PR2 and trying to let it help it know when it hits something. And we'd found that the gripper caused a lot of noise. Anytime the gripper was actuating, we'd get all this noise on our signal. And trying to figure out how to do that more intelligently. Basically, we would make models of what the robot expects to feel due to its own motion and then kind of cancel that out intelligently. And so whereas normally, actually, we'll just skip these, but normally you would hear a lot of noise and then we get rid of it and you can tell what happens. See, they're little spikes. Yay. Okay, oh, and then what's it good for? Then as the robot is moving the world, it can do a better job of knowing there's something in its way or and be able to tell, is this something, the thing I'm feeling, is it from my own motion or is it something that's a problem? And once your robot can do that, it's time to celebrate. And so we've also taught our robot how to do high fives. This is my first PhD student, Joe Romano. And then he said, Katherine, high fives aren't cool. Our robot needs to fist bump. And so we also taught the PR2 how to fist bump. And this is actually research. There are physical contacts happening. You couldn't do this based on vision and identifying the robot. If it keeps going through the high five, it's very awkward. It needs to react and pull back. And so again, we're using the sense of touch in human-robot interaction. But I don't have time to talk about a lot more of the details. But hopefully I've convinced you that we need haptic sensors, especially tactile sensors. We need to dig deeper into the data. And actually, the very last, I keep saying very last, but this is truly quick. When you look at images like these, you see physical properties, right? You can tell what that material is. You have an idea of how it would feel to touch. But robots, they see only shape and color, which is better than seeing nothing. But I think robots should be able to anticipate mechanical properties of objects from a distance, as humans do, because that will help them in their physical interactions with the world. So if you were to reach out and touch an object or walk across a surface, you would use your estimates of the mechanical properties, even though you don't realize you do this, all the time to better control your motions. And robots don't do this, so this is a new project that I'm working on with Trevor Darrell. We're trying to connect vision and learning with haptic sensation and motor control. And the idea, we've made this big data collection system where we can go around and probe lots of surfaces and collect dense visual and depth data of what the surface looks like and then associate that with what it feels like. So then robots shouldn't have to touch every surface in the world. They can just download this library and see carpet or see glass or see wood and know, oh, if I touch that, it will be hard and it will be high friction and it will be bumpy, and then I can better anticipate what I will feel when I touch it so I can disambiguate and correct errors. So some sample data. So these are my main ideas. We need to go beyond force, dig deeper into the data, and connect cross-sensory modalities, so vision with touch. And then I think we'll be able to have robots that can do a lot more useful work in the world. These are all the great students and collaborators who contributed to the work that I've shown you today. So I want to thank them and the funding agencies who made it possible. And thank you for your kind attention.
We've got a little time for questions. Are there any questions from the floor? There's one over there.
Thank you very much for the interesting stories. I think it's both related to you and the previous Professor Anders presentation. For sensing or detecting the environment or interaction between a human life environment, now the vision is most advanced. And you are developing the touching or mechanical sensors. Mm-hmm. How about the other sensor like the hearing or the conversations or smelling or even tasting?
Great question. So you're right, vision is the most developed sense of touch, or sense. Audio, there is a lot more in like recognizing speech or figuring out who is talking to me. There's surprisingly little work on giving robots a sense of hearing, like for task completion. Actually, I had a part in a DARPA project before the DARPA Robotics Challenge, a different one called Autonomous Robotic Manipulation Challenge, and we gave our robot ears and had it listen to tell if it was actuating the stapler, if the stapler had actually, and it was hugely beneficial because the hand is out there in front and it had very limited tactile sensing. But I think there's room for improvement, more that could be done with audio. Again, it's picking out what's the signal versus what's the noise. If a robot's going to operate in the real world, there's a huge variety of background noises, distracting things, and isolating what's coming from the task and what's coming from the people I'm working with versus the extraneous signals. This is important. I haven't heard about robots that smell or taste much, but perhaps there would be a benefit, perhaps chemical sensing for robots in disasters. I can see places where that might be beneficial.
I think can I follow up?
Sure.
I think there's a
question, another question?
I'll take David first, and then there's a question at the back.
I can talk more.
Yeah. Great talk. That was a great talk. Thank you very much. I couldn't help wondering, where are we with skin? Right, because skin is fantastic, but getting all the sensors in there, you end up with lots of wires. And,
skin is fantastic.
Right, and is there I guess my real question is there a we're not going to make skin as good as this, right?
Not
yet.
Yeah.
Yeah. So is there a halfway house, and what might it be that would get us on the journey?
Yeah, so this is an interesting area for improvement. Some others are working on. I haven't been developing skin myself. We've been more doing the accelerometers, things that are deeper. We use the biotach. I like it because there are all these other constraints. It has to be robust, right? If this problem is if you put the sensors right on the surface, and then it can get damaged with interaction with the world. And so we've used the biotach to great success because it's more protected and robust. And so I'm kind of intrigued by things in that direction, but I've seen some cool sort of more fabric-based or panels or fusing. I think we need to think it's not just any one technology. I think we need a few different kinds of sensors and lots of them. But yeah, robotics can get to be kind of a painful exercise in wiring and signal processing, but we need more sensory cues. And as we're going toward that, I think we just need to be clever about what sensors we do invest in and thinking of a little bit non-traditionally in that way.
Okay. I think there was a question at the back there.
Please.
All right. Thank you very much. It's a fascinating talk. My background is in organ transplantation, and we're in the process of setting up the UK robotic transplant program. And I think this work you're doing is going to really improve patient safety. I just have a quick question. One of the operations we do is called hand-assisted laparoscopic donenephrectomy, where we have one hand inside the abdomen to dissect, and then we use laparoscopic instruments to take out the organ prior to implantation. So I was just wondering if some of these tools that you're developing can be applied to simple laparoscopic instruments to improve our sort of tactile sensation, essentially.
Yeah, and so the project that I showed with the milling machine and the sensor, the idea would be we would place that sensor on the end of a laparoscopic instrument or a version of that, so that we wouldn't need the hand-assisted, that we wouldn't need the larger incision for the surgeon to insert his or her hand into the abdomen, that we could have a laparoscopic tool that has a distribution of sensing on it, and then we could either in real time convey that to the surgeon. Visually has been done some before, tactily, or maybe an artificial intelligence where you palpate across. I think that yes, those are things we're working on. I have a grant from Intuitive Surgical and work I didn't show today, but also on palpating in robotic surgery and how to convey that information in real time to the surgeon. So I can talk to you a little more about that work.
I have, actually, I have to be the last question, I'm afraid. Actually, I actually have one question. Actually, so it's from the web system. And the Da Vinci robot actually been used for quite a while,
yes.
about 15 years. Can you actually say anything about the type of techniques that you've got here? Has that improved?
Yeah, so you're right. The Da Vinci robot, actually my PhD advisor at Stanford was one of the first engineers in Intuitive, and they've been doing that kind of surgery since 2000. I think the patents from Intuitive are going close to expiring, and so they've had a domination of the market, and there hasn't been as much change. But I think there are a lot of small companies who are interested in robots. I was talking yesterday to Guangchang Yang, who's in the Hamlin Center for Medical Robotics here in London, and they are doing many cool things with smaller robots, sort of also in the shared autonomy, so adding a little bit more autonomous than not completely do the operation yourself, but some subsets. So I do think we're on the brink of a big expansion in terms of what technology is available in medical robotics. I think it's been stifled from patents recently.
I'm afraid we don't actually have any more time for any other questions, but obviously the speakers are actually here, so please take the opportunity. Can I ask you to thank all the speakers today?